Okay, so this will be the course on superstring theory. So let me begin by briefly reviewing the action for bosonic string theory and covariant gauge, and then we'll try to generalize from there. So bosonic string worldsheet action. So this was given by minus 1 over 4 pi alpha prime. Where xi was the coordinates tau and sigma. Okay, tau goes along the worldsheet time, sigma is along the worldsheet space direction, sigma is compact. Okay. And these are diagonal matrices. So eta alpha beta is diagonal minus 1 1, and eta mu nu is diagonal minus 1 and then rest 1. Okay, the minus 1 of this. And then we had a constraint that we have to have T alpha beta equal to 0. Okay. Now, this was, of course, not the starting point of formulating bosonic string theory. Okay, we had started from a worldsheet diffeomorphism invariant action and then gauge fix to get to this form. Okay. And then we had to go beyond by introducing the ghost associated with the gauge fixing. Okay. So all those we will do later. Okay. So for now, we just think of this as some intermediate step in the quantization of bosonic string. Okay. And we are going to generalize this to formulate superstring theory. Okay. Then we will go back and see where it came from. So superstring theory. This supersymmetrizes the worldsheet action. Okay, and I'll explain what we mean by supersymmetrizing the worldsheet action. So here mu nu run from 1 to d, right? Mu nu runs from 0 to d minus 1. Okay. So we add to the bosonic string theory action an extra term. So this will be given by minus 1 over 4 pi alpha prime integral d to xi. Then we have the usual term. Where these are two component fermions. So psi mu here is two component fermion, psi mu plus and psi mu minus. Okay. Mu nu still run over d values 0 to d minus 1. And the rows are the gamma matrices. So we'll choose row 0 to be, these are 2 by 2 gamma matrices, 0 minus I 0, and row 1 to be 0 I 0. Okay. So they satisfy rho alpha, rho beta anti-commutator as minus 2 eta alpha beta. Okay, so rho 0 square is 1. Okay. Rho 1 square is minus 1, okay, which is consistent with this, and rho 0 and rho 1 anti-commutator. Okay, because this is sigma 2 and this is I sigma 1.
A choice of 2D.
Yeah,
Gamma matrix.
exactly. It's just a choice of 2D gamma matrices. Now, so from this you have the Dirac equation, which is rho alpha del alpha psi equal to 0. So this I can write as 0 minus I del tau plus I del sigma I del tau plus I del sigma 0 psi plus psi minus equal to 0. So this tells us that del tau minus del sigma psi minus equal to 0 and del tau plus del sigma psi plus equal to 0. And now if we recall the light cone coordinates, the definitions, u was tau minus sigma, v was tau plus sigma. So del u was half using this we see that del u of psi minus equal to 0 and del v of psi plus equal to 0. Okay. So as a consequence of equation of motion, psi minus is a function of u only, sorry, v, and psi plus is a function of u. Okay, but this is only when equations of motion are satisfied. Oh, yeah, I did. So this is true for each mu. Is this clear? Now, one can also interpret psi plus minus as chiral fermions. And that is because the analog of the gamma matrix, which in this case we can call rho 2, is rho 0, rho 1, which is basically 1, 0, 0, minus 1. So you see that rho 2 on psi plus psi minus is psi plus minus psi minus. So we call psi plus the right chiral and psi minus the left chiral. And this name also can be seen from here. The psi plus is a function of u only, right? And u is tau minus sigma. So it represents a right moving wave, right? If sigma increases and tau increases, then keeping tau minus sigma fixed, then the waveform remains unchanged. And similarly, psi minus will be left moving waves. Okay, but all these are on shell. Okay. Chirality, of course, doesn't require on shell condition, right? The chirality, the fact that psi plus forms an eigenstate of rho 2 with eigenvalue 1, right? That doesn't depend on whether it's on shell or not, whether it satisfies the equation of motion or not. The second point is that if we look at the Dirac equation, I rho alpha del alpha, this is a Dirac operator, right? Because or minus I rho alpha del alpha. But the important point is that this is real. Okay, because rho 0 and rho 1 are both purely imaginary. Okay. And so this means that psi plus minus can be taken to be real. And when I say it can be taken to be real, okay, this means that if we start with an initial condition where psi plus and psi minus are real, then the equations of motion will keep them real. Right? That's what is meant by saying that they can be taken to be real. The time evolution will not introduce complex numbers. Okay. So we'll take psi plus and psi minus to be real. So these are also Majorana form. So we will call psi plus a right moving right chiral Majorana file. That is Majorana because it's real and it's vile because it's chiral. Okay, it satisfies the gamma phi project, gamma that rho 2 projection, and psi minus will be a left chiral Majorana file. So in superstring theory, we have both psi plus and psi minus, but later we will see that when we go to heterotic string theory, right, we only have psi plus and no psi minus, okay, or vice versa. They are of course equivalent. And important point as these are all Grassmann odd psi plus minus, right, or psi mu and psi bar mu are Grassmann odd. I should have written the definition of psi bar mu. So psi bar mu is psi mu dagger gamma naught, sorry, rho naught. Okay, I'm writing rho because later on we'll introduce the gammas, the 10-dimensional gamma matrices or d-dimensional gamma matrices. Okay, so which should be distinguished from the 2-dimensional gamma matrices. So this is psi mu dagger rho naught. But if this is real, I can write this as psi mu transpose rho naught.
are real because of our choice of the gamma matrices, right?
No, no. It's just these choice of gamma matrices, the equations of motion are real, right? So this is what is called a Majorana representation, right? Where all the gamma matrices are purely imaginary. Right? In the Majorana representation, right, the reality the Majorana condition is just reality. Right? In a different representation, you will have to use a different condition for psi plus minus 2a Majorana. They will not be real, but their complex conjugate will be related to the original components by some additional matrix product.
Here, for these choice of gamma matrices, psi plus minus being real
is the Majorana condition. Right? For a different choice of gamma matrices, you can still define Majorana fermions, right? But there's relation will be more complicated. Why? Because you want to minimize the number of fields you have to introduce. Right? It's just a choice. Right? This is what defines the theory. Right? When you construct a theory, right, you have to specify what kind of fermions and bosons you add. I have chosen to add Majorana fermions.
I mean, you were choosing to add a minimal number of fermions to the original boson theory that you had.
Well, minimal is a somewhat tricky statement because the minimal would be Majorana unfiled, right? I could have just said psi minus equal to 0. That's not what we are doing, right? In heterotic string theory, we will do that. But in superstring theory, we need the Majorana condition, but not the file condition. That's the definition of the worldsheet theory.
Theoretical level question.
Yeah.
So this, when you argued by looking at the Dirac operator, that it is real under the evolution.
It will remain real.
Under EOM, it will remain real, so we can choose it to be real. But in path integral, will there be configurations in which maybe it turns complex?
Yeah, in path integral, of course, you can do many things, right? I'm saying that in the in the definition, if it was not, if the equation of motion was not preserving reality condition, right, we cannot put a reality condition on the fields, right? That will not commute to the Hamiltonian, right? Here, the reality condition commutes with the Hamiltonian, right? So you are allowed to put a reality condition. It's the same for bosonic fields also, right?
But this probably is just we want to make the theory well defined classically.
No, even if you don't put the reality condition, theory will be well defined classically. It will just have double the number of degrees of freedom, fermionic degrees of freedom. Right? You could have also taken x mu's to be complex variable, right? And written them x mu bar x mu. Right? I mean, we are not doing that. Right? So it's just our choice. I mean, what kind of worldsheet theory you begin with? Sorry, you had a question?
No, I mean, why would we integrate over complex variables? I mean, if we take them to be real, we only integrate over real rational variables. Right?
Oh, but often in quantum field theory, right, you may choose to integrate over complex slices. Right? It's by Cauchy's theorem, right? You can deform contours, and instead of integrating along the real axis, you can just integrate along some complex contour. So that possibility always exists. Any other question? Okay, so now I'm going to describe a supersymmetry or worldsheet supersymmetry to be more precise. No, I didn't take them to be that. This is that when they satisfy equations of motion, then they are like that, right? But as a field, they are functions of both U and V, right? As an off-shell field, they are functions of both U and V. Right? Equation of motion forces them to have that form. Right? This was like BC, right? The BC ghosts were taken to be only a function of U, right? But that was a consequence of equation of motion, right? The action for BC ghost, for example, was B del VC, right? And then the equations said del VC equal to 0 and del V B equal to 0. Right? So when you do path integral, right, we are not going to restrict to psi plus and psi minus being functions of U and V only. Any other question? Okay. So supersymmetry. So we take a constant spinner. Okay, the fact that you have written the plus minuses are upstairs and minus hours plus next is just a matter of convention, right? This is not very important, but it's a useful way to keep track of what combines with what. So this epsilon will be a Grassmann odd. Epsilon plus minus are Grassmann odd variables. And exercise to check delta S equal to 0 under the following transformation. Let me write an epsilon symbol because this is a parameter, infinitesimal parameter. These are infinitesimal. Okay, so while checking the symmetry, so while checking this condition, you keep only terms linear in epsilon. Is the statement clear? Okay. And you have to use epsilon plus minus are also real. And this is important because otherwise these transformations do not make sense, right? I rho alpha is real, right? Because rho alphas are purely imaginary, right? So I rho alpha is purely real. Okay. So x's are real, right? So epsilon better be real, otherwise psi plus minus will not be real. Okay. So you have to impose the condition that epsilon is real. Okay. With that, you should be able to show that under this transformation, delta epsilon s is equal. Okay. And for this, you have to also use the Grassmann odd property of these various fields. Okay. So, for example, you will encounter things like epsilon, let's say epsilon bar psi, epsilon bar psi mu. Sorry. This is epsilon dagger rho 0 psi mu, right? Okay. This I can write as epsilon transpose rho 0 psi mu. Because epsilon is real. Okay. Now I can do a transpose. A transpose MB is B transpose M transpose A, right? That's the standard transpose, except that here, when you take the transpose, because you have to switch the position of psi mu and epsilon, you pick an extra minus sign. So this is minus psi mu transpose rho 0 transpose epsilon. Now, rho 0 transpose, you can see from the definition of rho 0 transpose is minus rho 0, right? Because it's antisymmetric. Psi mu transpose is psi mu dagger, because psi mu is real. So this I can write as psi mu dagger rho 0 epsilon, which is psi mu bar epsilon. So we need identities like this to manipulate the various expressions that you will get by using these on the action that you have written here. Where is the action? This is the action. Is this clear, this statement? So this is called supersymmetry because it's mixing bosons with fermions. Right? Transformation of boson is proportional to a fermion, and transformation of a fermion is proportional to a bosonic combination. Okay, of course, it's made Grassmann out by multiplying by these Grassmann out spinors. Are there questions? Another exercise. Delta epsilon S is 0 if we take epsilon plus to be function of u, epsilon minus to be function of v. Okay, this is again straightforward to check. Okay. But I mean, if you want to check this, it's most useful if you rewrite this original action in front, instead of writing in this covariant form, you write in terms of u and v derivatives and psi plus and psi minus explicitly. Right? Then it will become clear how to prove this. The proof becomes easier. Okay? So rewrite this action in terms of uv. This, for example, right, will just be proportional to del u x mu del v x mu. Right? That's what we are saying. This because of this two-dimensional in the UV coordinate two-dimensional metric is purely off diagonal. Okay? And similarly, this also simplifies when you write in terms of u and v. Right? This one, for example, you will get a term psi plus del v psi plus. Okay, or psi plus transpose del v psi plus. Right? So from that it's clear that the equation of motion for psi plus will be del v of psi plus equal to 0. Right? And similarly, there will be psi minus del u psi minus, right? And the equation of motion will give you del u psi minus equal to 0. Okay, so the action actually simplifies. Instead of writing in this covariant form, you write in the UV coordinates.
But the transformation you have defined that we are not saying anything, right? It's just saying that they are here.
No. Here, they are constant spinors. Constant spinors, right? The original statement for the supersymmetry was epsilon plus minus a constant spinors, right? But now what we are saying is that you can also take epsilon plus to be a function of u and epsilon minus to be a function of v, and it's still asymmetric. Okay? And this is essentially a generalization of conformal symmetries that we had in bosonic string theory, right? If you just look at the bosonic string action, the symmetry is translation. The worldsheet translation is symmetry. You can translate tau by tau plus a and sigma by sigma plus b, right? And you can also write this as u going to u plus a constant, v going to v plus a constant. But then you know that u going to any arbitrary function of u is also a symmetry, right? And v going to an arbitrary function of v is also a symmetry. So these generalizations, right, the fact that you can take epsilon plus to be a function of u and epsilon minus to be a function of v is a generalization of the conformal symmetry that we have in the worldsheet theory.
Generalization in what sense?
That they are u and v dependent transformations. Just like in that case, you could take u to be an arbitrary function of u, right? And that was still a symmetry. So as an infinitesimal transformation, it was u going to u plus epsilon of u, right? So the infinitesimal transformation parameters are functions of u. And there is another set of infinitesimal transformations which are functions of v.
So general worldsheet symmetry is a combination. We said that.
Yeah, these are exactly. Yeah, it will be a combination of this and that. Right? These are symmetries and those are also symmetries.
For the algebra to be super-Virasoro.
Yeah, so this will make this into a super-Virasoro algebra. Right? So far we have not talked about Virasoro or super-Virasoro, but this is indeed going to make it into super-Virasoro algebra.
It will be like n equal 1 or n equal 2. Which are extension?
This is what called n equal to 1, 1. 1, comma 1, because in 2 dimensions you count left and right separately. Okay, there is one supersymmetry on the left, one supersymmetry on the right. Any other question? Okay. So right now these are just observations, right? That this particular theory has this property. Another property for constant epsilon plus minus, if you calculate delta epsilon 1, delta epsilon 2, x mu. Okay, so this is basically, so this is the definition is delta epsilon 1 delta epsilon 2 x mu minus delta epsilon 2 delta epsilon 1 x mu. Okay, and in this calculation you keep terms up to order epsilon 1 epsilon 2. Okay. This is given the exercise. This is given by A alpha del alpha x mu, where A alpha is 2I epsilon 1 bar rho alpha epsilon 2. And if we apply it on psi, delta epsilon 1, delta epsilon 2 on psi mu, this is also given by same A alpha del alpha psi mu. Okay. But here we have to use equation of motion after using rho alpha del alpha psi mu equal to 0.
Constant epsilon.
Yeah, for constant epsilon.
What we are applying?
That for psi, when you have to prove this.
But when this epsilon del epsilon x on psi, we obtain x, right?
Yeah, you obtain x, but there are the point there are also in that process some psi will also be involved. Let me just try to check. Okay, I don't now remember what equation of motion you need, but you have to use equation of motion. I think you need the psi equation of motion. But okay, this is something you can check. Okay. But the important point is that in getting to this result, okay, that delta epsilon, yeah, so delta epsilon to psi mu will give you x, but when you delta epsilon 1 on that, it will give you back psi, right? And you have to check that that combination is exactly this. Okay. And this happens to be true if psi satisfies its equation of motion. So we say that the algebra in this case closes on shell. Right? So supersymmetry algebra is that the commutator of two supersymmetry transformation is translation, but in this formulation it closes only on shell when psi equation is satisfied. Yeah, that a commutator of two supersymmetry transformations should generate translation. Right? That is supersymmetry algebra. Pardon? Well, it just happens to be that. Yeah. On shell. Right? Now there is a way to modify this theory by adding what is called auxiliary fields, where the algebra closes off shell. Right? But we will not really need to do this here. No, then you don't need the COM. Once you introduce auxiliary fields, then you don't need EOM.
It's that F, right?
Yeah, exactly. You have to use an auxiliary field F, and then equation of motion is not needed. Okay, but for our purpose, you don't need the auxiliary fields. We can keep it like this.
If I start from superspace, I'll get that. Right?
Yeah. If you start from superspace, you will automatically get the auxiliary. Is this clear? Are there questions?
What's the motivation for keeping it closed off shell as well? Like,
Sorry, I cannot hear.
can you hear me now?
Can you speak a little louder?
Can you hear me now?
Yeah, okay.
Yeah. What is the motivation to keep the algebra closed off shell? Like it's right now closed on shell, but you said we can have to add some auxiliary field. Is there any reason we will like to do it? Or?
Yeah, the reason is that if you want to modify the action, suppose you want to add other terms to the action, right, which also preserves supersymmetry, then it's much easier to do if you have an off-shell formulation in which the algebra closes off-shell. Because here what will happen is that if you add new terms to the action, the supersymmetric transformation laws themselves will get modified. Whereas in the off-shell formulation, the supersymmetric transformation laws are not modified, right? But you just add new term in the action which are supersymmetry invariant by themselves.
I see. I see.
Easier to generalize the action by adding new terms if you have an off-shell formulation.
Okay, thank you.
Okay. But not all supersymmetric theories have off-shell formulation, right? In fact, in the target space, right, most of the supergravities that we know in 10 dimensions and lower dimensions are formulated only such that the algebra closes on shell.
Then there is superspace description for those theories.
There is something called partial superspace, but not full superspace description. Or sometimes you may have to introduce infinite number of auxiliary fields, right? Something called harmonic superspace. I mean, the formulations are quite complicated. Okay, and let me just add here that if instead of taking constant epsilon, okay, you had taken the epsilon plus being a function of u and epsilon minus being a function of v, right, which is the general, which are more general symmetry transformations. Okay. What we'll get on the right hand side are the Virachora generators. Okay, are the transformations where the translation it will still have this form. Okay, but A alpha will now be dependent on the space-time coordinates. Right? In particular, AU will depend on U coordinate and AV will depend on V coordinate. Right? Because U will get translated by a function of U and V will get translated by a function of V. Worldsheet coordinates. Yeah, U and V are worldsheet coordinates. That suppose, so this is a special case when epsilons are constants, right? And you can prove this. Okay. Now I said that there is a more general symmetry in which you take epsilon plus as a function of U and epsilon minus as a function of V. So you can use those symmetries and try to calculate the commutator. Right? If you take the commutator between one epsilon plus and one epsilon minus, that commutator vanishes. Right? This you can check. But if you take two epsilon plus, okay, which are both functions of U, right, you will get a translation, but the translation generator will be a function of U. Right? And that is like a Virachora transform. right? More general conformal transformation. So that's the sense in which these are super Virasoro algebra. I mean, these symmetries basically generate super Virasoro symmetries of this worldsheet theory, where you have some worldsheet supersymmetric transformation that depends on U and V separately, and then they generate the Virasoro generators.
Expect to get something like AU2X.
Something like that, yeah. Okay. So on or acting on every field, right, it should be of this form, right? If delta x should be some A alpha del alpha x, right, where x is bosonic or fermionic, it doesn't matter. Okay. The question is what A alpha is, right? That A alpha is a complicated function of, here for example, A alpha was given by this simple form, right? In general, A alpha will be complicated functions of the U's or V's, right? And that will depend on what kind of functions the epsilons were. Is this statement clear?
Let's say this seems to be, I mean, some sort of, I mean, epsilon 1 and epsilon 2 are two supersymmetric transformations.
Yes.
But I mean, the commutator represents, I mean, carrying out those transformations in two different orders.
Yes.
But it seems to differ by a conformal transformation. Right?
Yeah.
Can we identify the conformal transformation uniquely?
Yeah, because Euler formula like this. See, this, for example, generates what translation you have uniquely, right? Given epsilon 1 and epsilon 2.
Yeah.
The same is true there.
Let's say I take like I take two such supersymmetric transformations. Both of them are kind of epsilon plus 1 and epsilon plus 2 are functions of U, epsilon minus correspondingly functions of V. So I can identify a conformal transformation of the worldsheet that will kind of correspond to the difference between carrying out in both of them in two different orders.
Exactly.
So this is how we've extended the Virasoro.
Yeah, this is how you have extended the Virasoro algebra. Right? So it's not just that this has worldsheet supersymmetry, it also has this extended Virasoro algebra, super Virasoro algebra, this theory. Okay, now T alpha beta. Earlier, you had defined T alpha beta as we had started from an action where you have worldsheet metric coupled to the x's, right? And you had defined T alpha beta by taking the derivative of the action with respect to the worldsheet metric, right? Delta is delta gamma alpha beta. But T alpha beta we can also think of as the Noether current associated with space-time translation in this gauge fixed theory. Right? That's the second way of introducing what T alpha beta is, right? Is as a Noether current associated with translation invariance on the worldsheet. Okay, so T alpha beta, let's think of it that way. So T alpha beta is Noether current associated with translation symmetry on the worldsheet. Okay, so using that we can calculate T alpha beta, and I'll leave it in the exercise to check. The T alpha beta as a form A alpha beta So C is an arbitrary constant because overall normalization of T alpha beta is not fixed. Right? That depends on how you normalize transition. So this part you will recognize, this minus the trace part. This is what we had in the bosonic string theory. Right? The effect of the extra fermions is to add this extra piece. Okay, because every field will contribute to the energy momentum tensor. So it's not surprising that the fermions also contribute to the energy momentum tensor.
That bosonic string theory.
Yes.
There is a string and it has coordinate x mu, then you write the induced metric on the sheet and so on.
Yeah.
These Fermionic coordinates, they have some interpretation.
Yeah, so we'll come to that interpretation, right? Right now, we are simply saying that let's take the covariantly quantized bosonic string theory, right, and try to generalize it, right? Then we'll see where it came from, right? I'll not go through the details, but I'll at least mention where it came from, right? Right now, it's just a straightforward generalization of the gauge fix theory. Is this clear? Now, similarly, J plus these are the Noether currents. Okay, that is the definition. Right? Why are there two? Okay. Because there are two independent components of the spinors, right? Epsilon plus and epsilon minus. Okay. Corresponding to that, we expect two independent Noether currents, okay, which we will call J plus alpha and J minus alpha. Okay. The procedure for finding this is the same, right? The standard Noether procedure. Right? The only thing you have to be careful about is that the epsilon sometimes can anti-commute with the various fields. So you have to keep track of the epsilons. Is this clear? Or should I? You remember how you define Noether current for a given symmetry? how you define Noether current for a given symmetry. Usual Noether procedure, yes. So that's what you have to remember. Nothing fancy. Yeah. So the usual Noether procedure, right? You have to use to find out what the Noether currents are.
So J plus and J minus correspond to epsilon plus and epsilon minus?
Yeah.
Or the other way around?
No, J plus corresponds to epsilon plus and J minus corresponds to epsilon minus.
Order is changed then.
What?
Just the choice.
Order doesn't matter. That's the overall sign, right? And again, as I said, the overall signs of the Noether currents, I mean, overall normalization is not fixed, right? Because if a current is conserved, any multiple of it is also conserved, right?
Then he is saying plus is yes, now.
Yeah, it's upstairs. Here, that's true. Because it's the epsilon, when you think in terms of the generator, right? The generators are given by epsilon times the integral of the Noether current, right?
So it has to be
So,
contracted.
yeah. So epsilon, that's why epsilon with upper plus will be accompanying G alpha with lower plus. Alpha is the space-time index, right? Del alpha, G alpha is 0. Right? Yeah. So del alpha, G alpha plus minus is 0. This is the conservation law.
Alpha is space-time.
Space-time, yeah. So alpha we are using for space-time, right? Two-dimensional space-time, not worldsheet space-time. Yeah. See, the point is, these didn't carry any mu index, right?
Yeah,
No mu index. So the J plus minus will not carry any mu index, right? But it will carry plus minus index because there are two symmetry transformation parameters. And it will always carry a worldsheet space-time, worldsheet index, right? Just like the A alpha or T alpha beta, right? There is a translation, right? Corresponding to that, there is a two index object, right? Because del beta T alpha beta is 0. So that's this index alpha. And I'll write down the expression for J plus minus.
So this minus plus and plus minus, these things being inverted is this the metric gamma alpha beta being off diagonal, right?
Yes. Yeah. I mean, there's the chirality index, basically. So let me write this G alpha. Plus minus index is implicit because it's a psi is a two component spinor, right? So when you apply this gamma matrices on the two component spinor, you get a two component object. So those are the upper and lower components. Okay, and again, this should be really a proportionality constant because overall normalization is not fixed.
Oh, JLK is proportional.
Proportional to, yeah, proportional to. Is this clear? Right? So rho beta rho alpha is diagonal, right? Because rho is off, rho 0 and rho 1 individual are purely off diagonal. Right? So this quantity is diagonal. Right? So you see that G alpha plus is proportional to psi plus. Right? Psi mu, I have erased that. Psi mu, if you remember when I wrote, the top component was plus, bottom components are minus, right? So J mu plus or G alpha plus is proportional to psi plus and or some derivative of, okay, psi plus times some derivative of x mu, and J minus is proportional to psi minus. Okay. And exercise del V of J plus. Okay, let me. So J basically the statement is that J plus is analytic. Okay, maybe this I'll come back later. Okay. That even though it looks like J plus alpha, right? J plus actually has only one component. Okay, which is J plus V. So J plus U is 0. They all of them follow from here. Okay. This is on shell. This is on shell, which means when equations of motion hold, J plus U is 0 and J plus V is non-zero. Okay. So we have the equation del U J plus U plus del V J plus V is 0, right? This is a conservation law. Okay. Now J plus U is 0. So this tells us that del V J plus V is 0. Okay. So J plus V is a function of U only. This is the analog of the statement that T lower UU is a function of U. Okay, because Virasoro generators are better be analytic. Okay, this translated to TZZ being a function of Z only. Okay. So J plus V is a function of U, and similarly J minus U is a function of U. And J minus V is 0. Okay, these all follow from this relation over here. Is this clear? Okay, so now we come to string theory. How do you construct a string theory out of this theory, right? So far, it's a two-dimensional quantum field theory, right? So in the case of bosonic string theory, right, what was special about string theory, okay, which is not in general true for arbitrary two-dimensional conformal invariant field theories, is that we impose the condition T alpha beta equal to 0. Right? That came from the some gauge invariant version, right? But net upshot was that we have to impose T alpha beta equal to 0 on the states or as a matrix element. Okay, which we eventually imposed by using ln acting on the state equal to 0. So if we only impose that condition, okay, to construct superstring theory, then we have not really done anything, right? Because you have added some extra psi mu's, but those are like some internal CFT, right? We saw that we can always add internal CFT in the to the theory. That will be equivalent to compactification, right? So if you are just using the T alpha beta equal to 0 condition, right, then it's exactly like ordinary bosonic string theory with some compactified extra compactification, okay, which are given in terms of CFT. However, the way the superstring theory differs from bosonic string theory, okay, is that we impose the condition not only T alpha beta equal to 0, but also J alpha equal to 0. So in superstring theory, impose the constraints T alpha beta equal to 0 and J plus minus alpha equal to 0.
Don't consider J alpha plus minus equal to 0.
Yeah.
Like it is compact.
Yeah, then it is like ordinary bosonic string theory with some extra part of the extra CFT added, right, to the usual X mu's. But that's exactly what we did for compactification, right?
Hello.
Yes.
The camera isn't moving, so I couldn't see what you wrote just now.
Here in this part of the board,
Yeah, on the left side of the board, whatever you wrote, I couldn't.
not coming.
It's not showing on the camera.
Camera has not moved. Okay, I don't know how to make the camera move. Let me see if I can. If I wave it, it's moving or no? Okay.
You should there and then slowly.
Okay. Okay. Let me see if that happens. I move here and then I slowly go to that direction. Camera is focusing on me. Okay, so now I slowly move. So no, it is moving. I think the camera is supposed to move. No. I mean, somebody is looking at it, but I think camera is supposed to move by itself. Has it moved or not? It hasn't moved.
It hasn't moved yet.
Okay, I think then we
If
have.
you stay out once he sees the screen, the person will move.
What?
If you stay out of the screen, then the camera person will be looking for you.
Oh, out of the screen. So how do I?
You are already.
Well, I'm already out of the screen. Okay.
That's when you write it.
But you can, if you want, you can use this part.
But
Oh.
I have a question.
Yes.
Maybe we can wait for that.
Okay.
I mean, T alpha beta equals 0 was, I mean, in BRST sense, what it will be. It was like a setting, we want to cancel the overall central charge, right? Somehow. That was the constraint there.
No, okay, that was not the concept. BRST invariance came from the original, quantizing the original gauge theory, right? Okay. So here also, we have not written down the original gauge theory, right? Which I have to tell you what it was, right? That T alpha beta equal to 0 came from there, right? As an intermediate step. And then we said once you introduce the ghosts, right, then you can forget about the constraints and reformulate the whole thing in terms of BRST cohomology, right? It automatically does the job. There is an exact analog of that here, right? Which I have not told you, right? I have not neither told you the starting point nor the final version, BRST invariant version that we are going to use.
There was this equivalence, right? This T alpha beta equal to 0 equivalent to the BRST.
Exactly, right? So similarly, here there will be some equivalence, right? This constraint, the T alpha beta equal to 0 and G alpha plus minus equal to 0, this constraint will be equivalent to the something, right? The corresponding BRST cohomology. But you have to set up the BRST cohomology.
This T alpha beta equal to 0 was the equation of motion for gamma alpha beta, the auxiliary
Yes.
metric that was.
Exactly.
So for the Nambu-Goto and Polyakov to be equivalent, this had to be the thing.
Yeah.
So that's why we introduced this constraint.
Yes.
But here this J alpha.
Yeah. So then I have to tell you where it came from, right? Okay, it still hasn't. It has moved. Okay.
It's focusing on.
Yeah, now it has started. It has moved.
Okay, so it's visible now. Okay. Okay. Okay, so any other question on this? Okay, so the question is, where does this constant come from, right? So for that, you have to go back to the starting point. to the proper starting point, okay, which I have not given, and I will not also give the details of, okay, but I will just mention how this constraint came in the first place. The proper starting point is to supersymmetrize the covariant gauge unfixed action, minus 1 over 4 pi alpha prime Okay, so this was the gauge invariant action. Okay. So we need to supersymmetrize this. Okay, that's where the superstring, the formulation of original formulation of superstring theory begins. Okay, so I'll not write down the action that one gets by supersymmetrizing this, but that it should have a symmetry of the kind that I described, where now epsilon is an arbitrary function of the worldsheet coordinates, right, of sigma and tau. First thing. Yeah, but that is not enough, because that thing has symmetry when epsilon plus was a function of u and epsilon minus was a function of v. Right? Here you are demanding that the epsilon plus and epsilon minus both should be functions of u and v, and it should still be a symmetry, right? Because you have to have a local symmetry, right? So this requires introducing psi mu's and also chi plus alpha, chi minus alpha. These were in some sense the partners of the x mu's. These would be partners of gamma alpha beta. Okay, because once you want that the full thing should be supersymmetric, then delta gamma alpha beta should be something, right? Epsilon bar times some fermionic object, right? And then that fermionic object will transform into gamma alpha beta.
So in this action we have diffeomorphism, so we want super diffeomorphism.
Exactly. So you want super diffeomorphism.
That action didn't have diffeomorphism because it was gauge fixed.
Exactly.
There it was not.
Exactly. Right. That's so the gauge fixed action that I gave had neither diffeomorphism nor super diffeomorphism. Okay. These actions should have both diffeomorphism and super diffeomorphism. Okay. And that required that we should introduce partners of x mu's but also partners of the gamma alpha, right? Which happen to be two component spinors like this. Right. So each component now also carries a worldsheet index. Pardon? Well, you can call it fermionic metric, but this is like the generalization of the radiator swinger. Spin 3/2 field, right, in 4 dimensions, carry a spinor index and a space-time index, a vector index, right? This is exactly like that.
Worldsheet gravity, no.
Worldsheet gravity, no. This is like worldsheet gravity, no.
But here it's like a gauge symmetry that we are supersymmetrizing.
Exactly.
But there it was not the case. Right?
No. Right? There it was not the case. Right? Here it's like gauge symmetry that was supersymmetrized. Is clear? So that we can write down an action, which I am not going to write, but the action will have these components, these fields. Okay? Besides this, you will have psi plus minus mu and chi plus minus alpha.
That would be residual.
Which, yeah, the one that you saw will be residual gauge symmetry, right? But this is the full gauge symmetry. So this has the symmetries, the gauge symmetries of this. So let me list those. So the gauge symmetries are diffeomorphism. These are all in the 2D sense. Local supersymmetric. In fact, even if you don't demand any local supersymmetry, imagine that we start from this action, which has diffeomorphism, right? And now we say that we just try to supersymmetrize it, preserving diffeomorphism. Okay? Just rigid supersymmetry, constant parameters. Okay? Then what is going to happen is that now if you take the commutator or anti-commutator between the supersymmetry, the constant supersymmetry transformation and the diffeomorphism, okay, it will generate some new fermionic transformation. Okay? So that will automatically generate the super diffeomorphism. Similarly, if you take the commutator of the constant supersymmetry with the Weil transformation, it will generate what is called the super Weil. Okay. So once you have some local symmetries and you try to supersymmetrize it, right? Local symmetry which involves translation, and you try to supersymmetrize it. Okay. Supersymmetry automatically becomes local. Okay, because there's a commutator of rigid supersymmetry with diffeomorphism will be local supersymmetry. Local supersymmetry.
I see that. That means introducing rigid supersymmetry is enough.
Yeah, introducing rigid supersymmetry is enough to get all these extra symmetries.
But this is not always possible that we have diffeomorphism, we can supersymmetrize it.
It may not be always possible, right? Not all diffeomorphism invariant theories can be supersymmetrized, right? But this one can be. Right? One can explicitly write down these fields and write an action which has local supersymmetry.
You just have to write some Rita-Schwinger kind of action for this kind.
Exactly. Yeah. So that you have to write the action for psi, right? Coupled to background metric, coupled to gamma alpha beta, right? To a stress tensor. Right? And then an appropriate action for the Rita-Schwinger field coupled to the, again, 2D metric.
But you're saying that I can just write all of those terms by demanding invariance in the rigid supersymmetry.
Yes.
And I won't get anything extra if I demand local supersymmetry.
No, you'll automatically get local supersymmetry. Yeah. Okay. That's why people say that if you have a theory of gravity, which you know we have, right? And if you have supersymmetry, right? Then you have to have local supersymmetry.
I mean,
Right?
that's the same statement. Supersymmetry must be gauged.
Exactly. Yeah. Because translation we know is already gauged, right? Because gravity is gauge theory.
Is it because supersymmetry, two supersymmetry transformations give translation, so local supersymmetry will give some kind of diffeomorphism?
Yeah, that you can think of it that way. And the algebra is such that you cannot have global supersymmetry once you have local diffeomorphism. So you will have all these symmetries, okay? And one can show one can show, one can gauge fix by setting at least locally. Okay. And this is the gauge fixed action that I wrote.
Where we don't even have some theory that has global supersymmetry.
No, because global supersymmetry will automatically imply local super. Look, you can have theory of global supersymmetry, right, which doesn't have gravity. Once you have gravity, yeah, once you have gravity and diffeomorphism, it will automatically have local supersymmetry, and those theories don't exist above 11 dimensions.
That's how we prove that for the greater than 11 there is no.
That's how many. Yeah, this is the ingredient that you have to have local supersymmetry, right? And you don't have. I mean, there are various constraints that you can derive, right? And using that, we find that you cannot construct above 11 dimensions. Okay. So once you fix gauge, we have to still worry about the gamma alpha beta equation. This gives you T alpha beta equal to 0. And the chi plus minus alpha equation give you J plus minus alpha equal to 0. So that's the origin of these extra constraints that we had found. Okay. So we are not going to go into this details of how exactly we get this. Right? We'll take this as a starting point. Okay. Later on, right, when you do BRST, we'll go back a little and then we also introduce the ghosts. Right? Because now once you fix gauge, you also have the super ghosts. Right? Besides B and C and B bar and C bar, you'll also have a set of super ghosts. Using the super ghosts and the matter fields, you'll construct the BRST current. And then the whole thing can be reformulated as a statement in BRST homology. Is this clear? Okay, and in this language, the symmetries, the super Virasoro symmetry is the residual gauge invariance. And that basically says that the local supersymmetry transformation has not been fixed completely. Because if it had been fixed completely, you wouldn't get epsilon plus as a function of u generating symmetries, right? You wouldn't even get the rigid supersymmetries if you had really fixed out the symmetry completely. Okay? So that is the residual gauge symmetry. Okay, and that's what is responsible for the super Virasoro symmetry that we saw.
Here also some kind of light cone.
Yeah, here also some kind of light cone gauge fixing is possible, right? But maybe we will not discuss it because it's useful for constructing spectrum, but not for interaction. Right? Covariant form is useful in some sense that for as far as spectrum is concerned, it makes it manifest that it's a Lorentz covariant spectrum. Right? But it has unphysical states that you have to remove by these constants. Okay, and these constants will be again implemented as matrix element, right? Just like in the case of bosonic string theory. Now there is one more ingredient that we have to learn before we actually try to construct the spectrum, and that is the following. So when you have a usual bosonic string propagating, right, we think of this as a map from the worldsheet to the target space. Right? We draw a worldsheet and imagine this being embedded in some target space, right? A string moving in space-time. Now, besides the x mu's, we have this psi plus minus mu. We can regard them as some additional directions in space, in the target space, right? Even though they are Grassmann variables. Right? They are Grassmann directions in the target space. Is that clear? Right? So the target space then you can write as some x mu in this direction, psi mu plus minus. This is of course multi-dimensional space. Okay, but roughly you can think of it this way. And the worldsheet is moving, is a surface embedded in this target space. Is clear? Now it turns out that in order to write down a consistent string theory, okay, and by consistent I mean now that we really don't want any tachyons or any unwanted particles. Okay, in order to get a consistent string theory, it is not enough to construct the motion in a target space of this form. Okay, we have to change the target space. Okay. And the way we change the target space is by saying the following. The actual target space is the quotient of x mu psi mu plus psi mu minus space by Z2 times Z2. Okay, by a 4-dimensional group Z2 times Z2. How does it act? Okay. The first Z2 takes x mu psi mu plus psi mu minus 2x mu minus psi mu plus psi mu minus. Second Z2, let me call this Z2 prime, takes x mu psi mu plus psi mu minus 2 x mu psi mu plus minus psi mu. Is statement clear? So the string is moving in a quotient. Okay, not in the x psi plus psi minus space. That's my definition of what string theory is. Okay. See, this is something that I have to specify, right? What is the target space in which the string is propagating? Okay. All these constructions are not affected by this because these are local, right? In the field space. Okay. Now I'm saying that in the field space you make an identification and we say that the actual target space is this. Now, what this means is the following. Okay. There are two consequences of this. Imagine that you are trying to find a wave function of the string. Okay. So the wave functional of the string will be a function of the functional of the x mu's and half of the psi mu pluses and psi mu minuses, right? If we say that the string is actually propagating in this quotient, right, then it better be that the wave functional is invariant under this transformation. Okay? Right?
Already you are in this portion.
Yeah. Imagine that we have a line, right? And you take a quotient, right? Which is half line. Basically, you remove that part, right? Then x goes to minus x. Then out of the original wave functions, right, only those which are invariant under x to minus x will be allowed. Right? Those which are odd under x to minus x will be thrown away. Right? The same thing is true here. Is this clear? So we introduce these Z2 generators. Yeah, certainly. Unless in the action, not only in the action you have this Z2 symmetry, because these constraints are also the Z2 symmetric, but I'll come to that later, right? It's invariant under Z2. Okay. These things, for example, change sign under the Z2, but J plus equal to 0 is the same as minus J plus equal to 0, right? So the constraints themselves are invariant under the Z2 symmetry. Right? Otherwise, you couldn't do this.
We have to.
If you don't do it, you don't get rid of the tachyons. You don't get rid of the tachyons. You want to get rid of the tachyons, right? So if you want to do that, then this is something that you have to do. Okay. So introduce two Z2 transformations, -1 to the FR generates psi plus mu to minus psi plus mu, and -1 to the FL generates psi minus mu to minus psi minus mu. Okay. So the physical states S must satisfy -1 to the FR on S equal to S and -1 to the FL on S equal to S. Is this clear? Right? If you are saying that you should identify points in the field space, right? Even though this identification is acting on the Grassmann variables, right? Nevertheless, it's identifying points in the field space. It better be that all the wave functions are invariant under that identification. So that's formally it's written by saying -1 to the FR on S equal to S and -1 to the FL on S equal to S. This is what is called the GSO projection.
That satisfies these two constraints.
Yes, you have to still impose this. Yeah. Is this clear? But there's another effect of this identification. Okay. So let me explain it using a diagram.
Sorry, what is FR and FL?
So these are two the -1 to the FR is by definition generates this transformation. Okay. So FR you can think of as a Fermionic number which counts only psi pluses.
Right.
Right? So FR is 1 for psi plus, right? Even number of psi plus will give you FR is even. So -1 to the FR will be 1.
Okay.
On the operators, right? But this is a statement on the states, that on the states it should satisfy this condition. So let's draw this x mu, psi mu plus. And maybe another direction psi mu minus, which we will not worry about right now. Suppose you have a point in this field space. Okay. And imagine that the closed string, okay, at sigma equal to 0, okay, has this value of the field in the field space, right? X mu at 0 and psi mu at 0 is given by this. Okay. Then the string can wind around, but at sigma equal to sigma plus 2 pi, it comes back to the original value. Is this okay? But this is not the only possibility. There is another possibility that it winds around and lands on its image. This point changes the sign of psi mu plus, right? But at the same point as this one. Because in the field space, we have identified the points x psi plus with x psi minus. X psi with x minus psi. Okay? So this is also a possible configuration of closed strings. Is clear? So in terms of boundary condition, this means that psi mu plus at tau sigma plus 2 pi could be psi mu plus at tau sigma or psi mu plus at tau sigma plus 2 pi could be minus psi mu plus of tau sigma. Okay? Both are closed strings, right? One in the original space before quotienting was closed in the original space, right? Other one was not closed in the original space before quotienting, but it becomes closed after you identify these 2 points. So these are known as the Ramon sector states, and these are known as the Neveu-Schwarz or NS. Okay, so this is shorthanded for this is R and this NS. Okay. So it is not a choice whether that you have to include both Ramon and NS, right? Once you have said GSO projection, right, which means you have already identified in the field configuration space these 2 points, right? So after that you have no choice but to include both sectors, right? Pardon? Both should be same. Same meaning what? True, but not they need not be equivalent, right? That this spectrum of this string may be different from the spectrum of that string. Yeah, imagine a circle, right? I'll give an example. Circle is the flat space modded out by translation by a lattice, right? Okay. Now consider closed string on a circle. Okay. Suppose compact target space is a circle, right? The string can, in the original flat space, right? The string can begin and end at the same point, right? Or it can begin at one point and end at a point translated by a lattice vector. Both are closed strings. Right? The first one has winding number 0. From the circle viewpoint, right? The first has a winding number 0. The second one has winding number 1. Right? These are different spectrum. Right? Both have to be included in the final spectrum, right? As we saw in the when you have a compact direction, you have to include all possible winding sectors. Right? This you can think of as a quotient of a line. Right? On the original line, the only states were just closed strings which begin and end at the same point on the line. Yeah, when you mod out, you have a choice that it ends, the beginning and end are not the same point on the original space, but they are translated by a lattice vector on the original space. It's like that. Right? So the actual spectrum will be defined, you have to include both. Right? This you can think of as the analog of the, so in Nebuchadnezzar sector you can think of as the analog of the winding sector, right? But in this Grassmann direction. Okay. And independently, we have these two choices for psi minus. Independently, so you have four sectors. Okay. One where both psi plus and psi minus are periodic. Okay. That is a Ramon-Ramon. Second, when psi plus is periodic, psi minus is antiperiodic. That is NSR. We write psi plus on the right because psi plus is right moving. Right? So that's why psi plus attributes we write on the right. Then you have RNS. Okay, this is when psi minus is periodic, but psi plus is antiperiodic. Okay. And then you have NSNS, where both psi plus and psi minus are antiperiodic.
Those are four different cases for boundary conditions, right?
Yes.
Not for configurations, right?
Four different choices of boundary conditions. For each boundary condition, you have the whole spectrum of states that you have to study. Okay. And on each of these sectors, you have to impose these GSO projections. Right? So GSO projection, what it does roughly, that it keeps 1/4 of the states because you are imposing 2Z2 projection condition, right? This one multiplies by 4, roughly, right? Because you have 4 sectors. Right? So overall, it gives the same number of states, right? Again, roughly, but GSO projection projects out states and the different sectors increase the number of states.
We don't do GSO projection, then there is no need to take account both sectors. We can
Yeah, if you don't do GSO projection, then you cannot take both sectors. Because when you are taking both sectors, that means you have already identified these points, right? And if you have identified those points, that means you have to impose that condition on the wave function. The wave function should be invariant under that transformation. Right? So it is not a choice, right? That if you use GSO projection, you have to identify, you have to allow for more boundary conditions. Or if you allow for more boundary conditions, you have to impose GSO projection. Right? These two go hand in hand.
GSO projection is equivalent to that quotient, right? I mean, that quotient.
GSO projection and this together is equivalent to that quotienting. Right? Once you do the quotienting, you have to do both. Right? You have to use GSO projection because wave function should be invariant under that transformation. But you also have to use these different sectors because now closed strings can begin and end at its image point. Right? It's just like when you have a compact circle, right? You have two conditions which have to go hand in hand. One is you have to include, you have the momentum is quantized because the wave function has to be periodic along the compact direction, right? But at the same time, you have to include the winding modes because you have to allow the string to end at the image points, right? Because you have identified, you are demanding invariance under x goes to x plus a. Right? So you cannot quantize the momentum and not include winding modes, or include winding modes and not quantize the momentum. Right? Those will be inconsistent theories.
The GSO projection -1 to the power FR plus FL goes to.
True, yes.
Then we don't have to take all the 4.
No, then not only that you don't have to, you cannot take all the 4 sectors, right? Then the only sectors you will include are NSNS and RR. Right? Because imagine that both are periodic, you start from both being periodic. Right? Then the only identification that you are making, right? is not that individually you can switch the sign of psi plus and psi minus. You have to switch the sign of psi plus and psi minus both. Okay. So that is also an allowed GSO projection. Right? Consequently, you have so you impose here minus 1 to the FL plus FR, right? Because that Z2 transformation is a simultaneous change of sign of psi plus and psi minus. But here then this boundary condition should be accompanied by this one, and this boundary condition should be accompanied by this one. So only NSNS and RR sector states will be included. Only on single Z2. Okay. So these are called type 0 theories. Okay. These are inconsistent in 10 dimensions in the critical dimension, but in one dimension, right, using Liouville, you can get a sensible theory, sensible type 0 theory.
Sensible and
Noether, yeah.
But here we will have to consider all four of them, right?
Yes, so superstring theory, you consider all four of them. Yes.
Whether-
Yes.
And these will also satisfy that property.
Yeah, so these will also have to satisfy that property.
So actually, I mean, before the identification, the space of states will be very large. Hilbert space will be very large.
4 times. Well, before the identification, meaning, no, the space of states will not be very large, because the space of states roughly will be of the same order, right? Because after the identification, what you are saying is that you will reduce this GSO projection will reduce to 1/4, right? But you have 4 sectors, right? So the projection reduces by 1 to 1/4, but 4 sectors gives you 4 times as many states.
Seems like it's almost as if I have new closed strings, new type of closed strings.
Yes,
Close the orange one,
exactly,
which is like before quotienting that wouldn't have been the closed string.
exactly.
Okay. So my definition of closed string gets generalized.
Meaning you have to generalize it once you quotient, right?
Yeah. So that is in process, I get more closed strings as well.
Exactly.
And that reduces.
Yes.
So the number remains same.
Yeah. So this is the difference between string theory and field theory. If you are doing quantum field theory on a quotient space, right, then you impose this condition, the invariance condition, right? But there are no new sectors that you get, right? Because point particles don't have winding, right? You get the new sectors because of it's a string-like object.
Z2 is the analog of Z for the winding. And
Exactly. Z2 is the analog of in this case, Z2 plus times Z2 is the analog of Z for the winding. Okay? There it is an infinite dimensional group. Here it's a finite dimensional group, but the physics is the same. Okay? That once you have a quotient, you have to do both. You have to project and you have to include new sectors.
I think that didn't perform the identification, we only would have the Ramon sector, right?
Yes.
So because we performed the identification, earlier configurations that were open strings have become closed string configurations, right?
Yeah. I mean, with this, there are many problems, right? Because the interactions will not work correctly if you only had Ramon sector states, right? So there are various issues. So we need NSNS, but you can this type 0 projection can give you sensible looking theory, except that you will not get double tachyon, except in one-dimensional theories. Okay, so I think I'll stop here and continue on Thursday.